Hello. How's everybody? Did you have a good weekend? This is so strange. Let's see. How many people do we have on here? 1, 2, 3, 4, 5. Looks like we're missing 1 or 2 people, so we'll hang out for just another minute. What are we missing here? Let's see. I'm going to show you what it's like for me. So I can do it. So I hit the mute button. That's what it's like for me. Just all these faces. By the way, have you guys seen that video of the Zoom rock and roll video? Have you seen this? It's pretty great. It really is a good song too. Hold on here, I'll find it for you. No, that's not it. Okay, I'm posting it. I'll send it to you via email to watch after we're done because it's pretty great. Truly great. Music video. Okay. All right. Anyway, I'm sending it. All right. So let's get down to business here. Over the weekend, you were supposed to be reading the book, and hopefully you did. Wait, who is this over here? Gabe. Oh, maybe Gabe left. Either Gabe, you left, or I can't see your head because your camera's too high. Anyway. So how'd the reading go? Okay. You don't have to hold, some of you are holding up little handwritten signs. You know, down at the bottom, you've got the reactions button. You can just use that if you want. Thumbs up or thumbs down. Give me, how many of you want to give me a thumbs up for the reading? Okay, not everybody, some of you. You got to get on that. So a couple of you are taking the class for credit, for a grade, and most of you are taking it credit, no credit. But if you're taking it for a grade, you really want to get on it. And if you're taking it credit, no credit, which is the way I designed the class, remember that you have to do a reasonable job in all of the assignments. So turning in something crappy for your first draft, which is doing just a couple of days, doesn't get you over that bar. Okay, what else? So let's think. We started talking about. Oh, wait a minute! I got to plug in my computer. We started talking about groundwater over the weekend, right? So the first week was a little bit about the hydrologic cycle. It was about rivers and infiltration and flooding and that sort of thing. And now we're starting to talk about water once it's in the ground. And we're going to talk about groundwater mechanics mostly for this week, meaning how the water moves underground. And then next week, we'll start talking a little bit more about water chemistry and water policy and that sort of thing. Okay, so before we get started, we're going to do a group exercise today. But before we get started, does anybody have any questions about any of that stuff? I think you were introduced to the concept of hydraulic conductivity. Is that pretty straightforward?
Yeah.
What about Darcy's law? Hydraulic gradient, all of that sort of thing, right? I mean, it's interesting because the equation for Darcy's law, which is, I'll let you stop for a second. Don't look at your notes. I'll just let you think and see if you can remember what the equation for Darcy's law is. Anybody remember it? It's got really just three terms, right? It's the velocity of groundwater is equal to the hydraulic conductivity times the hydraulic gradient. And hydraulic gradient is basically just you can think of it like how high is the hydraulic head in one place compared to another place. And that basic relationship is the same relationship that you use to describe the flow of heat. So if you think about your house in winter, right? It's really cold outside and it's warmer inside, and the heat always wants to flow from where it's hotter to where it's colder, right? That's just a universality, or it just always happens. So the heat inside your house is always trying to flow from inside your house to outside your house because it's warmer inside your house than outside in the winter, right? So what's determining the rate at which the water flows at which the heat flows from inside your house to outside your house? It's exactly the same as Darcy's law. It's the thermal conductivity rather than the hydraulic conductivity. In other words, it's the ability of the wall to transmit heat, right? Just like it's the ability of hydraulic conductivity, it's the ability of the aquifer to transmit water. And it's the gradient, it's the temperature difference between inside the house and outside the house. So if you want to stop the heat from leaving your house, you can't do anything. Well, there are two things you can do, right? You can lower the gradient. You can reduce the gradient, temperature gradient from inside your house to outside your house. And you do that by reducing the heat in your house. You make it cooler inside your house, right? Yes, that makes sense, right? So if it's really hot inside your house and really cold outside, if you make it cooler inside your house, you lower the gradient so heat doesn't want to flow out as fast. And the other thing you can do is you put insulation in your walls to reduce the thermal conductivity. Okay, so the same is true with moving groundwater, right? If you have a big difference in hydrologic head, then the water wants to flow faster from the high head to the low head. And if it's able to flow easily through the aquifer, in other words, if the aquifer has a high hydraulic conductivity, the water will move through faster. Same thing as heat flow. Okay, so one thing that you should just constantly repeat to yourself, because it's so important when thinking about hydrogeology. It's a basic, very basic idea, but it's something you just need to drill into your head. And that is always, always, always water flows from high hydraulic head to low hydraulic head. Just that simple. You'll never go wrong. It just goes from high hydraulic head to low hydraulic head. Heat always goes from where it's hotter to where it's colder, right? Air always goes from where it's under higher pressure to low pressure. It's always just everything in sort of in thermodynamics, we say just flows downhill. That's the idea. Okay, all right. So that's really important for the little exercise that we're going to do in groups today. So where are we? So what else do we talked about hydraulic conductivity, we talked about porosity, we talked about Darcy's law, hydraulic gradient, confined and unconfined aquifers. We talked about those, right? And remember that a confined aquifer can be treated a little bit more like a water balloon, right? And that it's like a very rigid water balloon because it doesn't really change. Well, that water balloon maybe isn't a great example because it does change its shape. But unconfined aquifers are like a glass with some ice in it. And the more water you pour in, the higher the water rises in the glass. And the more water you suck out, the lower the water falls in the glass. So the thickness of the aquifer is constantly changing, right? The more water you add, the aquifer gets thicker because the glass is becoming fuller. With a confined aquifer, however, the thickness of the aquifer is fixed. It's a very porous, permeable aquifer capped on the top and the bottom by something much, much less permeable with a much lower hydraulic conductivity. And we call those layers aquitards because they retard the flow of water. And what rock type is the classic example of an aquitard? Just mouth it. I can't hear you. Say it.
Shale.
Shale. There you go. Thank you. Shale. So shales are very, very fine-grained rocks, right? They're made of clays. and they're pretty packed together. And so water just has a really hard time moving along them or across them. Water can still move through them. It just moves much, much slower through them than it does through the aquifer, right? Okay, what else? I don't know. Do you guys have any questions? Anything that you were unsure about? Yeah, Jake.
So why are shales like notoriously good for holding oil then, if they have bad porosity?
Yeah, so that's a good question. So shales are often associated with petroleum deposits because a lot of shales have a lot of organic material in them. And before the fracking revolution, which is really only about what 15 or 20 years old, right? Before that, it's called the shale oil revolution, oil shale revolution. Before then, there was all this oil in the shales, but generally the oil in the shales wasn't extracted from the shales. You waited until it migrated out of the shales, it being the oil, and then migrated up into these little geological traps, right? So places where the rocks were kind of bent and the water or the oil would kind of get caught under the bend, and you drill down and suck the oil out there. What fracking allowed people to do is to go into the shale directly and suck the oil out of that. And what they did, this is actually highly relevant to what we're going to talk about in the next couple of days. If you drill a well down into an oil well down into a shale and start pumping, it's like, you're just not gonna be able to suck anything out. It would sort of be like if you ever had a really, really thick milkshake and you put your straw down at the bottom and you suck and you get one big gulp of ice cream and then the well goes dry, the straw goes dry, right? That's sort of like sticking a well down into a shale. You can get whatever oil or water is right around the well will come out, but the hydraulic conductivity of the shale is so low that the water or the oil can't be drawn in from further away, right? So what they did instead was they drill down and they developed this technology so that when they get at depth, they can turn their drill and drill sideways underground, and they drill right through the middle of the shale, right? And then they frack it by injecting water, basically, or fluids under a really, really high pressure, and they send all these fractures running through it. And then when you've fractured the shale, you've increased its hydraulic conductivity, right? Because of all these fractures everywhere. Then you start sucking out the water, and then the oil comes with it. That was a much longer answer than you wanted, but that's what you get. So unless you're going to do something to the shale to increase its hydraulic conductivity, like fracture it, hydrofracture it, then it's a generally very, very impermeable layer. Got it? Okay. Any other questions?
I have a question about using for the water.
Wait, say that again.
Using for the water table. It was in the 3-point problem.
Uh-huh.
How do you know that sorry, Dottie's barking. How do you know that like 920 would be equidistant from 910 and 930? What if the slope changes or something between those 2 points?
Yeah. Did I post the answers to those, by the way? To the 3-point problems?
I'm not sure.
No.
Okay, I'm sorry. I'll do that right after we're off here. So the question is, if you have 2 points on a map, like one's at, what were the numbers? 310 and 330? Whatever, 310 and 330. How do you know that 320 is halfway between them? And in reality, Eliza, what you do is you assume it. You assume that there's a linear change between 2 points, right? And I kind of mentioned this the other day. That works pretty well if you're talking about pretty closely spaced data points, and you're talking about things like water level. If you're talking about concentration, like how much gasoline is dissolved in the water, you generally wouldn't use linear interpolation. You'd use some sort of exponential function because the gasoline is probably diffusing away. So for our purposes in this class, we're always going to assume it's linear. So if it's halfway, if it's in the middle between 2 points, it would have half the value. if it's a third of the way over, it would have a third of the value, that sort of thing. Yeah, but it's an assumption that we're making just in this class. Any other questions about the work? And I'm sorry I didn't post the 3-point problems answers. I don't know why I didn't do that. Anything else? Oh yeah.
How much technical, like how much in our papers, how much do you want us to like talk about the book, I guess, like, and also talk about things that we're learning in class at the same time
Sure.
in relation to the book?
Yeah, right. But I mean, I think what I'm generally expecting is that your analysis of the book is based almost entirely on the book and is not reliant on any of you having had the lecture material.
Okay.
You're certainly welcome to bring it in, but you can do it without it.
All right. Thanks.
Okay, so we're gonna do a little exercise for the next 15 or 20 or 30 minutes, and I'm gonna divide you randomly up into groups again. If you go to Moodle, there is posted to Moodle just as of a half an hour ago or so, under exercises, something called leaky aquatard exercise. Wait a minute. Where is it? Is it not there?
I don't see it.
Huh.
It says there's been no recent activity.
I just did it. Let me try it again. I'll upload it again. Huh, it's weird. Okay, here goes. Let's see if it works this time. Okay, now it should be there. Leaky aquatard exercise under exercises on Moodle. You guys see it?
Yeah, there it is. You might have to refresh the page a couple times.
So this is a little exercise that allows you to apply Darcy's law and to think a little bit about hydraulic gradient and different kinds of aquifers and all kinds of stuff. All right. I think it's certainly doable. You're just gonna have to think it through a little bit, okay? And I'll bounce around and as I did before and help you out. So does everybody have it? Have you guys all found it and downloaded it? Yes? Okay. Sydney, you got it? Yeah, okay. All right, so I'm gonna divide you up into groups here. And if I can. And then we'll get back together and talk about it in a little bit. Sound good? Okay, so hold tight while I try to figure this out. Breakout rooms, there we go. So what did I do last time? 5 breakout rooms? Sounds about right, automatically. Would you rather have 3 people in a breakout room or 5? 5? Raise your hands up. Would you rather have 3 or 5? Looks like it's pretty evenly split here. All right, well, we'll go this way. All right, see ya. Did you guys get your invite? Hey guys.
Hi.
All right. So forget I'm here. I'm just going to be a fly on the wall.
Is Clayton here?
Yeah, I'm here.
Wait,
Hello.
Hey,
You guys are reading through the problem.
yeah.
Yep.
The trick to this problem is just making sense of it. And once you get a sense for what's going on, then the math is not a big deal. Okay.
Cool.
So read through it carefully and remember that water always flows from where to where?
high hydraulic head to low hydraulic head.
There you go. Okay, good. I'll be back.
Ooh. Activity.
I don't know what that is.
Do we need that for the equation?
Not sure.
Ron, do we need the vertical conductivity for the equation?
You do. Well, you'll need it for the problem. So where does water always flow from and to? Generic.
What do you mean from to?
Water always flows from blank to blank. What's the huh?
Is it high to low?
High to low what?
Heads.
High to low.
High to low what?
Points? Heads?
Heads, yeah, from high hydraulic head to low hydraulic head. It always flows there. Just like heat always flows from where it's hotter to where it's colder, high temperature to low temperature. So what you have basically is a box, right? And water is flowing in the front of the box and it's flowing out the back of the box. How do you know it's flowing in the front and flowing out of the back?
It tells you.
Okay. And would it be flowing anywhere else once it's inside the box?
Towards the bottom?
Why is it going to flow towards the bottom?
Because of the slope.
Slope of what?
The gradient, the hydraulic gradient.
Okay. So read me the part that says that there's a different hydraulic gradient.
Well, it just says the hydraulic gradient in the vicinity of each aquifer's inflow. Oh, wait. Let's see. The hydraulic gradient in the vicinity of each aquifer's inflow area is 0.1. So you're saying it's the same?
Okay, so let's back up. How do you calculate the rate at which water moves? How do you calculate the groundwater velocity? 2 words, 3 syllables.
Darcy's law.
Darcy's law. Okay, and what is Darcy's law?
It's the
It's Q equals the negative K over the multiplied by the hydraulic gradient.
Okay, so it's hydraulic conductivity, K, times hydraulic gradient, right? And so that'll tell you how fast the water's moving. What if you wanted to know what the volume of water is moving per second with volumetric flow, Q? How do you calculate that? Think of it like if it's a river. How do you calculate Q in a river?
It's
Did you just get your eyebrow pierced, Eliza? Is that new?
no, it's a year old.
Oh, okay. It looks like it's kind of bruised there, like you just got it.
is that the Is that the Manning equation?
No? How do you get volumetric flow? You take velocity, and what do you do with the velocity?
Oh, it's times the cross-sectional area, right?
Right, right. So it's velocity times cross-sectional area. So you have all these different cross-sectional areas here, right, in these boxes,
Mm-hmm.
and you can calculate the velocities. Agreed?
Is that where the vertical conductivity comes in?
It will, but you gotta think about what's actually happening here. So water's going in the inflow. Could
Yeah.
we calculate how fast water is moving at the inflow? What do we need to calculate the velocity of the water?
Well,
2 words, 3 syllables.
Darcy's Law.
Darcy's Law. And what are the 2 things that we need for Darcy's Law? Which you've already told me. I just want you to say them again.
the hydraulic conductivity and the hydraulic
Gradient.
Okay. And do we have those at the inflow?
well, we have the hydraulic gradient because that's the same, and then
Do we have the hydraulic conductivities?
yes.
Okay. So from that, we can calculate the rate at which the water is moving, right?
Mm-hmm. And then you just multiply that by the area.
Yep. And you can
So-
calculate Q, right?
Would you do the area of each little section, or is this as a total?
Well, each little section has its own different hydraulic conductivity, right? So you got to do each section on its own.
Okay.
What is
So-
1e minus 6?
What's that?
What is 1e minus 6 meters per second?
It means 1 times 10 to the minus 6 meters per second. Okay. So do those calculations and then think about this sentence, which I've given you, which is so important and is a hint to this problem, that water always flows from where it has higher hydraulic head to lower hydraulic head, right? So keep working on those calculations, and I'll be back in a little bit.
Okay.
Oh.
Hi.
Hello.
How's it going?
Okay, okay. So we're using this. So we're calculating what the gradient should be. Calculate the volumetric flow in and out of each. So in the aquifers, the outflow area, that's like that would be like kind of the change between the two aquifers.
Hold on one sec. So say that again.
So the inflow, so the water is moving through it parallel to the bedding layers, parallel to the
Mhm.
layers. Yeah, okay. So so the outflow we have to measure, we're gonna all right. I get that, makes more sense. Okay.
So you
So
have
we're gonna see how the speed of the water is impacted by going through the aquifer, and also how much water is being kind of either lost or gained in the going through the one layer.
there you go. You're way ahead of it. Okay, I'll leave you guys to work it through it. It's good.
Okay,
All right.
great. Wonderful.
Potential.
Yeah, yeah.
So the
good
higher
color.
potential in this area would be, or not potential, the higher pressure.
Head.
The higher pressure is on the lower one.
Oh, hi.
Oh, hi. So I'm having a little trouble figuring out what's indicated. So the 20-meter aquitard is the one with the 10 to the -9
Yep.
conductivity, and then the A and the B arrows are pointing at the 10 to the -6 aquifers.
Yes.
So that's the permeability of those.
Yep.
Okay. So because the pressure is being applied to the lower aquifer, the flow is upwards through the aquitard?
Because the hydraulic head is higher in the lower aquifer than it is in the upper aquifer.
Oh, then it had.
Water is
So-
flowing up,
Okay.
but it's also
So,
flowing
sorry.
out horizontally, right?
Wait, it is flowing out horizontally?
Yeah.
Is that what the inflow and outflow of the 0.1 gradient, hydraulic gradient?
Right. So the hydraulic heads, wait, what does it say?
Algae in the lower aquifer about 10 meters higher. So that's the difference in height for our equation here, the Q equals -K, that's the DH.
Yeah, hold on. Let me just look something here. I might.
10 over 20. So are we looking at an upwards flow of
Something.
1/2 times 10 to the -9? So the outflow is this way.
Okay, yeah. Yeah, so you can, so the front of the box looks like this, right?
Yeah.
And the water's flowing in.
Yep.
And then it's going through and it's going out.
Mm-hmm.
And you know that you can calculate the velocity that the water is moving. If you have the hydraulic conductivity, which is given for each
And the
unit.
1,000 meters and the oh wait, just the 0.1. We just need the 0.1, right?
Yeah. So think of this as think of the actual two-dimensional box right at the front where the water's going in.
Yeah.
Don't worry about the rest of the box. Just think about it right at the front.
Okay.
You can calculate how fast the water is moving right at that point because you know the hydraulic conductivity of each layer, and particularly the aquifers, right?
Okay.
And you know the hydraulic gradient, which is 0.1 right at that point. So then you just multiply hydraulic conductivity times hydraulic gradient, and you get the velocity of the water.
Yeah.
Does that make sense to everybody? Laura, does that make sense?
Yeah.
Gabe? Remember that Darcy's law, which is the little q, so the velocity of the water is equal to hydraulic conductivity, K, times hydraulic gradient, dH over dx.
Yep.
Okay. So if you want to calculate the velocity of the water at the very beginning, you just multiply the K times the dH dx, both of which are given. If you want to calculate the volumetric flow, big Q, what else do you need to do? Tommy?
The cross-sectional area?
You multiply it by the cross-sectional area that it's the cross-sectional area that it's flowing across. So for the aquifer A, what is the cross-sectional area at the start?
10 by 100, so 1,000?
10 by 100, which is 1,000 square meters, right?
Yeah.
Now, as the water is moving from the inflow to the outflow, as you guys rightfully pointed out, not only is it moving from the inflow to the outflow, it's also moving from where to where?
From B to A.
From B to A, because why?
The hydraulic head is higher in B than it is in A.
There you go. So the water most of the water is moving like this along the aquifer, but some of it, as it moves, is leaking up.
Okay.
Okay.
So you guys are on the right track. I'm going to leave you. You're doing really good, really well.
Okay.
And I will be back.
Okay. Thank you.
Yeah. Graham?
Yeah.
Hey, can you get it? You can't get into a breakout room, huh?
No.
See if I can assign you one here. I'm going to assign you to which one? Who were you in with before? Do you remember?
I was never in a breakout room.
Okay, I'm going to assign you to join 4. How do I do that? Assign to 4. Okay, you should see an invite now.
Okay. Thank you.
Come in. Oh, never mind.
What? Dissing me behind my back?
We're
I'm recording this. I'm on tape now. What's going on? How's it going?
we have really no idea what to do.
It's you're gonna look back on this having gotten through it, and it's gonna be just so crystal clear. But right now I understand that it's totally fuzzy. Okay, so you have this box. What do I have for a box? You have this box, right? Which is the thing that you're given, and it's divided up into all these different aquifers, right?
Mhm.
And the water's flowing in the inflow and out the outflow. Make sense?
Oh.
Do you see that in the image? Yeah?
Like it's going in on one side?
Yeah.
Okay.
Where it says inflow, see that arrow with inflow?
Oh, okay.
That's the direction the water's flowing into the box.
hmm
And then it goes parallel to that arrow, and then it comes out the back. You get it? Yes or no? I get it, I don't.
Yeah. Yeah.
So what we want to do is we want to calculate big Q. What is big Q?
The hydraulic flow rate or the volumetric flow
Volumetric
rate.
discharge, right? We talked about that in rivers as well. And how do you calculate big Q for a river or for anything?
You take
CFS, cubic feet per second, or gallons per hour, or whatever, volume per time. What do you do? How do you calculate that?
the cross-sectional area times the velocity of water.
Yeah. So you need to know how fast it's going, and then you need to know how big an area it's moving across. So the area is in like square meters. The velocity is in meters per second. And when you multiply square meters times meters per second, what do you get? Cubic meters per second. Volume per time, right? That's the volumetric flow. Agreed?
Mm-hmm.
Okay. So we can easily calculate the cross-sectional area perpendicular to the direction the water's flowing, because you're given all those numbers on how thick each unit is, how wide it is, and so forth. Right? But how do you calculate the velocity of the water? 2 words, 3 syllables.
Manning equation?
No. That's 4 syllables.
Darcy's law?
5 syllables. Darcy's law. So Darcy's law allows you to calculate the velocity of the water. And what 2 things do you need to know?
The hydraulic gradient and the conductivity.
And are you given those at the inflow for each unit?
Yep.
Yep.
Yes.
So you know that the hydraulic gradient at the start is 0.1. And you know the hydraulic conductivity for the aquifers is 10 to the minus 6 or whatever it is. Meters per second.
So it would be 10 to the minus 7 or negative 10 to the minus 7.
It won't be negative because the hydraulic conductivity is a positive number and the hydraulic gradient is a positive number, so it'll be a positive.
Oh.
That negative, remember the negative disappears You're right. In reality, they probably should have reported, I probably should have reported the hydraulic gradient as negative 0.1, but forget the negative. It always confuses people. So anyway, so you can calculate the rate at which the water is moving. K times dH dx. You multiply that by the cross-sectional area and you get how much water is moving into the aquifer at the inflow per second. So what'd you get? You multiplied, to get the velocity, you took 1 times 10 to the minus 6 meters per second. You multiplied it times K, by the hydraulic gradient, which is 0.1. And you get 1 times 10 to the minus 7 meters per second as the velocity. And then you multiply it by what cross-sectional area?
10 times 100 meters.
10 times 100. And so what is big Q for aquifer A and B at the inflow? (10 times minus 4 meters per second). All right, so you guys, I want you to write less and focus on what I'm saying here because I got to bounce around between different groups. So if you know how fast the water is going in, right? You know how much water is going in, you would expect to have the same amount of water coming out. The water can't hide in there anywhere. It's got to, the same amount that comes in has got to come out. Agreed?
Yeah.
If it was just a hose, that's what would happen. However, there's something else going on, and what's going on is in the third sentence where it says the hydraulic heads in the lower aquifer, which is B, are about 10 meters higher than in the upper aquifer. So as the water is moving from the inflow towards the outflow in the aquifers, what is happening?
So water's moving from the lower aquifer to the higher aquifer?
The water is moving from the lower aquifer to the higher aquifer because water always moves from
The high hydraulic head to the low hydraulic head?
Yeah, it always moves from the high hydraulic head to the low hydraulic head, and the hydraulic head is higher in the lower aquifer. So there's water leaking up from the lower aquifer into the upper aquifer. And you can calculate how fast that water is moving, again, using 2 words, 3 syllables. 2 words, 3 syllables.
Darcy's Law?
Darcy's Law, right. All right, that's it. Keep going. You're doing good. Hi.
Hi.
How goes it? You're the
Pretty
only one I can
good.
see. Crystal, Andrew, Joby, are you guys there?
Yeah.
Okay, I just get your video is not showing up for whatever reason. All right, so how's it coming?
Fine, I think.
Okay, where are you in the problem?
For some reason, for B, I'm getting 0.099 repeating meters squared for flow, and then for A, I'm getting 0.07 for meters squared for my flow.
So how are you calculating flow? When you say you're calculating flow, you're talking about at the inflow or at the outflow or where?
At the outflow. Oh, okay. I see what you're saying.
Me or somebody else?
No, you.
So how do you calculate flow at the inflow? How do you calculate capital Q at the inflow? For A.
It would be Q is equal to negative K times A times DH over DL. Or, yeah.
DH dx?
Yeah, DH dx, which would be the value given for the hydraulic gradient, which is given.
Okay, so hydraulic gradient at the inflow is 0.1.
Mm-hmm.
K, the hydraulic conductivity of aquifer A, is 1 times 10 to the minus 6.
Yeah.
And what is the cross-sectional area?
About 1 million cubic meters.
No.
This would be 10, no?
What is the cross-sectional area of A?
1,000 meters.
1,000 meters.
Squared.
So it's
Squared.
10 meters high by 100 meters wide, right? So that gives you, when you multiply all of those numbers together, 10 to the minus 6 times 0.1 times 10 times 100, that gives you capital Q at the inflow for A and for B. So the water is going from the inflow through the box, through aquifer A and B, and then out the back of the box. But is that the only direction the water is moving?
No, it's moving vertically too.
It's moving vertically too, because the hydraulic head is greater in B than it is in A. So how could you calculate the rate at which water is flowing from B to A?
Using the vertical conductivity of the confining layer.
And what else? What else do you need besides hydraulic conductivity?
How
do you calculate? What equation are you going to use?
The vertical hydraulic, no, I don't know.
Crystal, what equation do you use when you're talking about the flow of groundwater?
I can't answer that. Is it? It's not the same one?
Yeah, Darcy's law.
Is it? Oh, it's the same one. Oh, okay. I thought it was more complicated than that.
So you need
Cool.
to know what two things in order to figure out how fast water is moving, according to Darcy's law. Andrew, what are the two things you need?
His mic doesn't work, so it might
Oh.
take a second for him to just to let you know.
Well, Crystal, you tell me. What are the two things you need?
God.
What's Darcy's law, Crystal?
I have to recall. Is it area?
Well, one form of it has area in it, but just to know how fast groundwater is moving, what do you need? Little q. Jake, what do you need?
Hydraulic head and cross-sectional area.
Hydraulic gradient
Gradient,
and
okay.
hydraulic conductivity. K and dH/dx. Right?
And is there an A in that equation as well, the area? Or is it just Q equals minus K dH/dx?
Little q is K dH/dx, and that is the velocity of water. If you want big Q, you have to multiply little q by cross-sectional area.
Okay.
So big Q equals little q times capital A. And this is something we talked about last week as well. We were talking about calculating discharge in a stream. You need to know how fast the water is moving, and you need to know the cross-sectional area of the stream.
So what's the difference between little q and big Q? Like, what's the term you'd use?
Little q is groundwater velocity, And
Uh-huh.
big Q is volumetric flow or volumetric discharge.
Okay.
Okay, keep
Do you
plugging
take-
away. I'll be back. Hi, how's it going?
We got confused.
Yeah.
Okay, where are you?
So we think we found the volumetric flow for the inflow.
Okay, what'd you get?
Well, for A, I got 1 times 10 to the negative fifth.
For A?
Yes.
No.
Okay.
So the cross-sectional area you want is the box the water is flowing across. So what are the dimensions of the box the water is flowing across at the inflow for aquifer A, let's say?
Well, we did like a cross-sectional area, so I just did 100 times 10, but what?
That's it. So it's 1,000.
Yeah.
So the cross-sectional area is 1,000, all right? And what is dH dx? What's the hydraulic gradient?
0.1.
0.1. And what's the hydraulic conductivity of aquifer A?
1 times 10 to the negative 6.
Okay. So by multiplying K times the hydraulic gradient.
Oh, is it supposed to be to the negative 4?
Because it's centimeters?
Oh, no, I didn't even take that. No, I think I just wrote it down wrong, but is 1 times 10 to the negative 4 right for A, or is that still wrong?
For A?
Yeah.
For the cross-sectional area of A?
No,
For the volumetric flow.
Volumetric flow.
Oh, I see. Well, let's see. It would be 0.1 times 10 to the minus 0.7 be 10 to the minus 4. Yeah. Big Q is 10 to the minus 4 meters cubed per second for A.
Yeah. That's actually what we had. I pulled it off.
Yeah, that's what I had.
Yeah, I wrote it down wrong.
And that's also what you would get for B, right?
Yeah.
At the inflow, because they're the same?
Yeah. So then for the middle, do we use the vertical conductivity?
Yeah. So
The
water is flowing in the box. Think of this as like aquifer A, right? Water's flowing in here and out here. And you just calculated, if I turn it this way, you just calculated how much water is flowing past this surface every second. There's 10 to the minus 4 cubic meters of water flowing across this surface into the box every second.
Mm-hmm.
Okay. Now, it turns out there's another aquifer here down below it, and the two aquifers are separated by this aquitard, right?
Mm-hmm.
So you have a bottom aquifer, a top aquifer, and an aquitard in between them.
Mm-hmm.
And we know, because we're told, that the hydraulic head in the bottom aquifer is higher than the hydraulic head in the top aquifer, right?
Mm-hmm.
So what's going to happen between this aquifer and this aquifer?
The water is going to go, like, it's going to rise.
Because water always flows from
High hydraulic head to low hydraulic head.
high hydraulic head to low hydraulic head. So not only is the water going this way through the aquifers, some of it is leaking from the bottom aquifer up to the top aquifer at the same time. So now you just calculate the amount of water that's flowing up, again, using Darcy's law.
So we just plug in the vertical hydraulic number for the horizontal hydraulic number.
So you need hydraulic conductivity of the aquitard, which are given.
Mm-hmm.
That's 10 to the minus 9.
Yeah.
You need the cross-sectional area over which the water's flowing. And what would that be?
2,000.
No.
Well, because isn't it 20 meters?
Well, but the water's flowing up, right? So what's the cross-sectional area perpendicular to the direction the water's flowing?
1,000.
What's the length and what's the width?
100.
So it'd be 1,000 times 100.
1,000 times 100, yeah. That's the cross-sectional area. And then what's the last thing you need? Write out the equation. What's the
That-
equation for Q? Big Q.
Big Q. Oh, we need the velocity.
Okay, that's true. But if you break it down even more, big Q is just equal to so you know that big Q is equal to KA, right?
Mm-hmm.
No,
No,
sorry. Q times A, little q times A,
yeah.
right? So let me start over. Q is equal to K dH dx.
Mm-hmm.
Forget all this. And big Q is equal to KA dH dx.
Mm-hmm. What happened to the negative?
The hydraulic gradient I probably should have given it to you as negative 0.1.
Okay.
So anyway, yeah, the negative always screws people up. Don't get hung up on the negative. Okay, just you can kind of ignore it. All right, so what is if we're trying to think about how much water, big Q, look over here, how much water is migrating from the lower aquifer to the upper aquifer, right? So the flow is from B to A.
Mm-hmm.
You need to know the hydraulic conductivity of the rock that the water's going through. That's the aquitard, right?
Mm-hmm.
What is that? 10 to the minus 9. You need to know the cross-sectional area, which you already told me is 1,000 meters times what? 100 meters?
Yes.
And now you need to know the dH dx. And this is for you to puzzle through. How much does the hydraulic head drop by as you go from the lower aquifer to the upper aquifer?
10.
Okay, so that's the change in head, 10. What's the dx? In other words, over what distance does that drop in hydraulic head take place?
I think we tried it. It's 100.
Nope.
No?
No. You're close. Keep looking. I'll be back. Think about it. Over what distance does the drop in hydraulic head take place?
Hey, Leon.
How's it going?
It's going, oh, sorry.
Oh, no, go ahead.
It's going good. We're having a little trouble figuring out how to calculate the hydraulic gradient in the outflow area.
Okay, well, think about it in terms of Darcy's law. Let's write it this way. Should have brought my whiteboard up here.
Oh, I know exactly what you're trying to say. Yeah, because we now know the speed of it. And then all we have to do is calculate for delta H, the change in height.
Well, dH dx.
Yeah.
You want that whole term.
Yeah.
Oh, that's right, because that's the gradient. Yeah, so we would just calculate for that.
Right. So.
Yeah.
Okay. So do you have all of the other terms?
Yes.
Okay. All right, good. Excellent. I'll be back. I'm going to end the breakout sessions here in a minute anyway, and we can talk about it. Let's see if you can
All right.
knock out that final answer.
Great.
Hi, did you guys get it figured out?
So I think I've got it mostly figured out. We're trying to work through it with everybody. But so for the final, the sketch the general form of the potentiometric surface. So there's going to be two separate ones, right? One for each aquifer.
Right.
That considers like if you were to ignore one of the aquifers and just drilled straight to the other one, how high the head would be.
Mm-hmm.
Okay.
And you're going to use contour lines to show that. You don't have to calculate exact numbers. You just want to get the generic form for that.
Okay.
So in general, because the bottom one is losing volumetric flow, it's going to decrease over the course from inflow to outflow.
What's going to
Is that
decrease?
the height of the head? No.
Well, the height of the head has to decrease no matter what. As you move down gradient, the hydraulic head has to be getting lower, or else the water wouldn't flow that way.
Right. Okay.
But think about it. What's happening at the inflow, right? You have two aquifers, A and B, and they have the same amount of water entering the box at A as enters at B.
Yeah.
Right?
Yep.
But as you move through the box, what's happening? Water is migrating, is leaking from the bottom aquifer to the top aquifer, right?
Yeah.
Yeah.
And you calculated that amount?
Yes.
Okay.
Yep.
So that means then that even though the amount entering A and B is the same, at the back of the box, the water leaving A is going to be greater. Wait, greater or smaller? Which is the bottom one?
The bottom
Bottom
one
is
is
B.
B. The amount of
Yeah,
water
A is
leaving
good.
A, is going to be greater than when it started, and the amount of water leaving B is going to be less than when it started.
So I think I calculated the gradient at the outflow of A and B. How
Okay.
do I use that to translate into like the general height of the head?
You don't even need the calculation at the end to figure this out.
Okay.
Think about it. Let's see if you guys can see this. Can you see that okay?
Yeah.
So remember that Darcy's law says that the velocity of the water, which is Q, little q,
Yep.
is equal to K over dH dx. Right? That's the most important equation in all of hydrogeology, is that Darcy's law right there. And that big Q, which is the volumetric flow, is equal to little q times the cross-sectional area. Right?
Yeah.
Mm-hmm.
So we can rewrite that as big Q equals K A dH dx.
Okay.
Right?
Yes. Yeah.
So whatever's on this side has to equal whatever's on this side. So what's happening is, as we go from Q at, I forget now, is A in the bottom or the top? A is on the top. Okay. So as we go from QA at the inflow to QA at the outflow, Q is rising. This is higher.
Right.
Yeah, it's going up.
Outflow and lower at the start, right?
Right.
So if we're going to increase Q as we move along, we have to increase something on the right-hand side as well to max that, right? Are we changing the hydraulic conductivity as we move along from the inflow to the outflow? Are we changing the cross-sectional area?
Nope.
Nope. So you have to be changing the hydraulic gradient. And does the hydraulic gradient have to be going up or going down?
It's going up for A and down for B.
Right. So how would you depict that on a map? So imagine you have a map like this. This pen is kind of fading. I don't know if you can see it very well.
Yeah.
This is the inflow. We're looking now down from space on the top of the box. Okay.
Yeah.
Okay.
So what we had before was kind of like
That's more of a side view.
this.
Yeah.
Now we're looking down from the top. So if nothing changed, if you didn't have any leakage of water from one aquifer to the next, then what you'd have would be Let me do this a little bit better. You'd have each one of these lines is supposed to be a contour line showing the hydraulic head, right? And it's got to be going down as you go from the inflow to the outflow, right?
Yep.
If there's no leakage. But because there is leakage, the hydraulic head is changing.
So
The hydraulic gradient is changing.
Yes.
closer together.
So if you're gaining water, like aquifer A is, the hydraulic gradient has to be getting steeper and steeper as you go from the inflow to the outflow.
Yeah.
Oh,
So
You
what
have
would that
more
look
lines,
like
right?
in terms of these contour lines?
they'd be closer together by
Yeah.
the end of it.
Each one would be slightly closer to its predecessor than the previous one was.
Yeah.
Right?
Okay.
So like scaling. on it.
And for the aquifer that's losing water, right? Instead of these arrows pointing up, the arrows are pointing down. The outflow has less water than where it started, so the hydraulic gradient has to be decreasing as you move along.
So they get more spaced out for B then?
They get spaced out more, yeah.
Okay. That makes sense.
All right, I'm going to end the breakout here in a sec, so hold tight.
Sure thing.
I just realized you guys have a breakout room. I had to scroll down. I've been talking to everybody else over and over and over again. I'm so sorry. I feel terrible. How's it going? Did you figure it out?
No, we're kind of stuck.
All right. Well, rather than I feel terrible. My screen is set up and I was just going 1, 2, 3, 4, 5, and I didn't notice until just a minute ago that if I scroll up, I get to 6, and you guys are in 6. Hope there's not a 7. Jesus. Anyway, I'm going to end the breakout session rather than explain this to you guys separately and then explain to the whole group again. We're going to do it as a group. And I'm sorry that I wasn't able to help you along the way. But anyway, here we go. Let's see if I'll try and end this in just a second. Everybody's coming back.
Cool.
Okay, I think everybody is back. Does everybody have all of their group members here? Look, can you tell? Can you see anybody else?
Yeah.
You can see everybody else? So look around for the rest of your group members. If anybody's missing anybody, let me know. Because I don't know how to tell.
Hey, we got everybody.
Here.
Oh, more people are coming in. Okay. I think we must be good now. 4. Oh, there's somebody else. Okay. All right. So you guys did a really good job with this, and hopefully I know that for a lot of people, certainly for me, the first time I tried this problem, it just kind of, I didn't quite get it. I didn't quite understand what was being asked. But I think you guys have done a really good job, and hopefully it helps to sort of solidify some of these concepts of the way groundwater moves, right? So I'm just going to reiterate this one more time. Groundwater always moves from
high hydraulic head to low hydraulic
high
head.
hydraulic head to low hydraulic head. Everybody turn your mute button off so that I can hear you, so you can talk out loud. Unless there's something really noisy in the background, like a vacuum cleaner or something. Okay, so groundwater always goes from high hydraulic head to low hydraulic head. So what's happening here? Water's flowing in the front of the box and it's flowing out the back of the box. But at the same time, it's flowing from the lower aquifer up to the upper aquifer because water has a higher hydraulic head in the lower aquifer than in the upper aquifer, right? So you got to think of these two things happening simultaneously. All right, so let's go through this. Hopefully this will work. Okay, can you guys see?
Yeah, I can see the paper.
See that okay? All right, so the most important equation in all of hydrogeology is Darcy's law. which we're gonna not worry about the negatives and just do it this way. Can you guys see the blue? Does that show up, or do I need a different color?
Barely.
Barely? I had these really sharp, beautiful black magic markers, but they're dead now. Let's try this purple. Does this work any better? Oh, you know what? Here, I'll use plain white paper. That'll help.
It just seemed a little bit dark, is why I couldn't see it.
Okay. You see that?
Yeah.
Any better?
Yeah.
Hopefully. If it's not, I can run downstairs and get a different marker. Is that okay?
That works.
Okay. So this is Darcy's law in one dimension. And whenever you see little q, what that means is velocity. So this is the groundwater velocity. How fast does the water flow from point A to point B? It's determined by the hydraulic conductivity and the hydraulic gradient, dH dx. Right?
Mm-hmm.
Okay. Now, if we multiply little q times cross-sectional area, right, which is analogous to, you remember, oh boy, I'm getting in over my head here. If you have a channel like this and the water's coming out like that, right? That's groundwater that's the water velocity, how fast the water is moving in the stream. And if you want to know what the volumetric flow is, big Q, you would multiply the cross-sectional area of the stream times the velocity, and that would give you big Q. That's the way we did it last week. So velocity times area is volumetric discharge, right? And that's in like CFS, cubic feet per second or something. We're just doing the same thing here with Darcy's law. We have the velocity, and we multiply it by the cross-sectional area, and we get big Q, volumetric discharge. Okay? All right. So if we rewrite this, putting these values in for little q, we can write it like this. Q equals K A dH dx. I just snuck the A in between the Q and the dH dx. Okay? So these are two forms of Darcy's law that you will use all the time, that you will see all the time. And these are two things you got to commit to memory, right? They're just, it's like the alphabet for hydrogeologists, like counting to 10. It's everything. Okay. So at the inflow, at the front of the box in our problem just now, we have this aquifer here. Aquifer A and aquifer B, doesn't matter, they're identical, right? And each one is 10 meters high and 100 meters across, right? So the cross-sectional area at the inflow, which I'm going to shade in like that, cross-sectional area at the inflow is 100 times 10 is 1,000 square meters. Make sense? You got to shake your heads or something, but if you stare at me, I don't know what you're thinking. If it doesn't make sense, tell me. Okay. We know that the hydraulic gradient at the start, which is dH dx, is 0.1. How do we know that? Because we're told that. And we know that the K of aquifer A and aquifer B is 10 to the minus 6 meters per second. So now we have dH dx here, we have A here, and we have K here, and we can calculate the volumetric flow into the box for A and for B. Okay? And you get, what do you get? 10 to the minus 4, was it? I think. 10 to the minus 4 cubic meters per second. That's Q at the inflow. All right. Now, as the water's moving along, as the water's moving along from the inflow to the outflow, right? Water is not only moving from the inflow to the outflow, but it's also leaking across this aquitard in here. Why is it leaking across the aquitard? Because the hydraulic head here is higher than the hydraulic head in the aquifer above it. So some water is migrating up like this. How could we calculate how much water is flowing from the lower aquifer to the upper aquifer? How do we do that?
Darcy's law.
Darcy's law, capital Q again, right? So if Q equals, can you see? KA DH dx. What do we use for K? What is the water flowing through to get from the lower aquifer to the upper aquifer?
The aquitards.
The aquitard, and that has a hydraulic conductivity of 10 to the minus 9 meters per second times the cross-sectional area. What is the area perpendicular to the direction the water is flowing when it's going from the lower to the upper aquifer?
100,000.
It's 100 meters times 1,000
200,000.
meters.
No.
Right? And what is the DH dx? Well, we know that the hydraulic gradient, we know that the hydraulic head is 30 meters higher here than it is here, right? So the change in hydraulic head from here to here is
30
meters. And what is the distance over which that hydraulic head is changing?
It says it's 10 in the problem.
20.
It is the thickness of the aquitard. And this aquitard is 20 meters thick. So that's 20 meters.
I think the difference in the heads is 10.
Yeah, it says
That's
in
what
the
Scott
problem
was
the,
saying.
the difference is
Oh,
10.
oh, you're absolutely right. I'm sorry. Yep.
Yeah.
Thank you. 10 meters is the change in hydraulic head.
Yeah.
Yeah.
The heads are both 10, and then the aquitard is 20.
Yep. All right. So what would we get here? We get 10 to the minus 9 times 10 to the 5th is 10 to the minus 4th times a half. So that would be 0.5 times 10 to the minus 4, or 5 times 10 to the minus 5th cubic meters per second. I just multiply that out. So that's the amount of water. That number right there is the amount of water that's leaking from the lower aquifer to the upper aquifer. Okay? Everybody understand why it's leaking that direction? It always flows from higher hydraulic head to lower. So since there's higher hydraulic head in the bottom aquifer, some of it's going to leak out. All right. So almost done. So at the inflow, QA, the volumetric flow at A and aquifer A was the same as it was at B, right? And it was 10 to the minus 4 cubic meters per second. We already calculated that. But at the outflow, we know that QA has to be bigger than QB. Why does the water flowing out of aquifer A have to be more than the amount of water flowing out of aquifer B at the outflow?
Because they were the same at the beginning, but then B has been like leaking up into A.
Yeah, because B has been losing water into A, right? Vertically. Okay, so how high is the amount of water flowing out of A? The amount at the outflow is equal to the inflow plus the leakage, right? So we had, at the inflow, we had 10 to the minus 4 meters cubed per second, and the leakage is 0.5 times 10 to the minus 4 meters cubed per second, right? So we get 1.5 times 10 to the minus 4 cubic meters per second leaving through A. How much is going to be leaving through B?
Same amount.
No?
No,
It can't be the same amount.
Well, the same amount that was coming from B is now removed from B.
Right? So QB is equal to the amount it started with, 10 to the minus 4 cubic meters per second, but now we've lost 0.5 times 10 to the minus 4 cubic meters per second. This would be 1 times 10. So that equals 0.5 times 10 to the minus 4 cubic meters per second. That's the amount that should be coming out of QB. Does it make sense that this number and this number, when you add them together, right, should equal this 2 times this number? You're putting in a certain amount. You're putting in, let's say, 2 times 10 to the minus 4 cubic meters per second. What comes out the back has to be the same amount of water. And if you add these up, they equal what's going in. All right, last part of this. Remember the box looked something like this in the original problem?
He said he thinks he can do everything that today.
Right? You remember that? That's sort of what it looked like, right? What I'm going to draw you now is what you'd see if you were just looking straight down from space, just on that top rectangle. Okay? So here's the inflow, and here's the outflow back here. So I'm going to draw it like this. In and out. And we're just looking down on that top plane. Everybody see what I'm talking about? Okay. So if no water was leaking from one aquifer to the next, you would have a constant hydraulic gradient of 0.1. So it would be analogous to having a perfectly planar hill slope, right? The slope would just be perfectly planar. And if you're going to draw contour lines on it, the contour lines would always be the same distance apart, like that. With each one of these lines representing the hydraulic head, and the hydraulic head decreasing as you go from the inflow to the outflow. The hydraulic head, let me say that again, the hydraulic head has to decrease as you go from the inflow to the outflow, because if it doesn't, water won't be flowing in that direction. Remember, water always flows from high hydraulic head to low hydraulic head, so the hydraulic head has to be dropping as we go this way. Okay? All right. Now, what happens, let's go back and write Darcy's law here. Q dH dx. What is the difference for aquifer A at the inflow versus the A at the outflow? What is the difference between QA at the inflow compared to QA at the outflow? What is it?
It's higher at the outflow.
It's higher at the outflow, right? So Q equals KA DH dx. This has increased. The volumetric flow has increased as we've gone from the inflow to the outflow. So something over here has to increase as well, right? If you have an equation and you increase something on one side, you have to increase the other side by the same amount. Q has increased as we've gone from the inflow to the outflow. Has the hydraulic conductivity increased as we move? Have we suddenly magically changed the hydraulic conductivity of the aquifer? Shake your head, nod your head. What do you think? No. What about the cross-sectional area? Have we changed the cross-sectional area of the aquifer? No. So what we must have done is changed the hydraulic gradient. So for A, this is what it would look like if there was no leakage. Since there was leakage into A, since A is gaining more water, and more water gets added the further downwind you go, the hydraulic gradient has to become steeper and steeper as you move down slope. You see what I mean by the hydraulic gradient getting steeper? The spacing between the lines is getting shorter and shorter and shorter. So if it was a hill, the hill would look like this. It would be getting steeper and steeper and steeper and steeper the further you go along line.
So we're drawing it like a topographic map. Then.
Exactly like a topographic map. And if you were to look at B, that would be for A, right? Here, let me write that up here. This is Q, this is for aquifer A. And this is the height, each one of these is a line of equal hydraulic head. And then, so what would it look like for B? B, it would be just the opposite. You'd have something that looked like that, where the hydraulic lines are getting further and further and further apart. The slope of the hill, if you think of it that way, is getting flatter and flatter and flatter as you move, because it has less water that it needs to pump out of there. Okay, you get it? So this is being recorded, and I'll post it, and you can go back and look through it. But I don't know how you guys feel about this. Maybe you're just feeling kind of overwhelmed, or maybe you're feeling like, yeah, I get it. I wish you'd quit talking. But in either case, this is a really good, I think, illustration, a good example or problem to work through to help you understand the way groundwater flows and help you understand Darcy's law, right? It doesn't matter. It doesn't care if it's flowing up, down, right, left. It just wants to go from where there's higher hydraulic head to lower hydraulic head. That's all it cares about, it being groundwater. And in some cases, the water is essentially moving in two directions at once, right? It has these two discrete flow paths. There's a difference in hydraulic head between the inflow and the outflow that's causing it to move horizontally, and a much smaller hydraulic difference gradient between the lower aquifer and the upper aquifer that's causing it to leak up at the same time. And as the water gets added to an aquifer, as we can see from Darcy's law, the hydraulic gradient responds. Turns out that's going to be really, really important starting the day after tomorrow, when we start talking about what are arguably the most important parts of groundwater equations, which are those having to do with pumping wells. When you stick a well down into the ground and you start pumping water out of it, what happens to the shape of the water table and all that stuff, and the hydraulic gradient? And that's all really, really important. So it's good that you get this information now. Okay, so I'll stop talking. Do you guys have any questions about this? You just want to go and then look at this, look at the video and make sure you understand it? Okay, I'll let you go. I will post some homework for tonight based on this, and I will post the videos for you to watch for tomorrow. Okay.
Did you post the answer key to the other homework?
Yeah, I will. Yeah, thank you. And we're going to have another one of these sort of breakout session things tomorrow to do another exercise. Okay. Okay, that's it. Thank you, guys. If you have any questions or anything, you're more than welcome to email me or Zoom me or call me separately. But for now, for the group, I'll just sign off. All right. See you later. Be safe. Bye.